So what's got me intrigued right now is the difference between a description of the local bubble in A Beginner's Guide to the Universe and the description of the local bubble in Wikipedia. Now, why is it that they think the ultraviolet bubble is there? It's because gases and dust filling the spaces between the stars should observe virtually all shortwave ultraviolet radiation before it has a chance to hit Earth. But they have used a small telescope to detect extreme ultraviolet radiation from a few nearby very hot stars, which means basically there's a bubble where they can see ultraviolet, and outside that region, no ultraviolet. Now, the main local bubble that they've been able to identify is 40 parsecs wide, which is about 150 light years in radius, or 300 light years in diameter. I shouldn't say 40 parsecs wide because this doesn't cover the entire radius. It stops about 4/5 of the way out. But the center of it is right close to the sun. You can see the sun here, and here's the center. I should draw those in different colors. Yes, the sun here and the center right there. So this is not very far at all. Maybe 10 light years or so. Now, Wikipedia's diagram of the same phenomenon has appears to be more or less 3 different bubbles, one centered close to the sun, one close to Beta Canis Majoris, and one close to Antares. And unfortunately, neither of these two images share any stars other than the sun, so it's hard to get a measure of their relationship. But it says right here that the local interstellar cloud, the local bubble is at least 300 light years across, which puts it in the same size category as this one, which is 40 parsecs plus 40 parsecs. Now, both articles offer some information. So both of them give the diameter to be about 300 light years. But then on Wikipedia it says that the neutral hydrogen density is about 0.05 atoms per centimeter cubed, and the average density for the Milky Way is 0.5 atoms per centimeter cubed. Meanwhile, A Beginner's Guide to the Universe says that the bubble is about 5,000 atoms per meter cubed. Now, to convert that to cubic centimeters, we would need to divide it by 100 3 times. So it would be 500 times, or 5,000 per meter cubed times 1 meter over 100 centimeters cubed, which would be 0.005 atoms per cubic centimeter. Meanwhile, it also says the density of the interstellar medium is roughly 10 to the 6th atom per cubic meter, just 1 atom per cubic centimeter. So this is kind of interesting because by Pearson's account, the bubble is, or ordinary space is 200 times denser than the bubble space, and while Wikipedia's the factor is only 10 times as much. Now, another point that they agree on is the cause of the local bubble, and they both agree that it was some kind of supernova, most likely. Pearson says it was probably carved out by a supernova explosion that occurred in these parts roughly 300,000 years ago, while Wikipedia says it's the result of supernovae that exploded within the past 10 to 20 million years. Now, I think the difference between 0.05 and 0.005 could be almost a rounding error. Same thing with 0.5 and 1. Off by a factor of 10, no big deal. But between 300,000 and 10 million years is a factor of like 30 to 70 times. So are one of these explanations, the Wikipedia and Pearson, just wrong, or what? It's actually probably coming from two different hypotheses. In the Wikipedia article, we're clearing out about 90% of the material, while in the Pearson article, the explosion cleared out 99.5% of the material. Also, the Pearson explanation is a fairly recent phenomenon, while Wikipedia's explanation is very long ago. One question that I'm compelled to ask is, if this thing happened 20 million years ago, and 10 to 20 million years ago, and it's 300 light years across, how fast would it take, or how fast would a gas molecule need to go in order to cover that distance in that time? So using velocity equals distance over time, in both cases the distance is 150 light years. So in the first case we're talking 150 light years over 300,000 years. You can cross off years and we're just left with 150 divided by 300,000 times the speed of light. So this would give you the average outward velocity of the particles to create that bubble, 150,000 meters per second, or 2,250 meters per second. Now that would just be the average velocity that would be needed in order to create the bubble, depending on the time at which it was created. There's another piece of data that the Introduction to Astronomy has that Wikipedia doesn't have, which is that the temperature of the ambient temperature of the gas in this region is 500,000 Kelvin. Now this is not mentioned in the article on Wikipedia, so we have to kind of go on this, and we can do a bit of a calculation, because it is possible to calculate the root mean square velocity of gas particles based on their temperature and their mass. In this article, that's given as 3RT over m to the 1/2 power. But I think I've also seen it given as degrees of freedom over 2 times K sub B times T over the molar mass. I'll just write that as AMUs, which stands for atomic mass units, and that would all be taken to the 1/2 power 2. So to get this number to be as high as possible, let's use atomic hydrogen with mass of 1 atomic mass unit. Degrees of freedom for a monatomic gas is 3. K sub B is 1.38 times 10 to the negative 23rd times this crazy thing. That kilogram in there gives you the impression that we need to convert to a kilogram, but that's not true. This is just in joules per Kelvin. Joules per Kelvin. This kilogram meters squared per second squared is a joule. Really, the primary difference between R and K sub B is R is in joules per kilogram Kelvin. K sub B, or R is in joules per mole Kelvin. K sub B is in joules per particle Kelvin. Okay, I've gone out to Wikipedia to look up root mean square speed, and it looks like I've got these reversed. This version of the equation needs to be in kilograms, and this one needs to be in atomic mass units. And so we are not going to use this number. We're going to keep things simple, use 8.31. R equals 8.31 joules per mole Kelvin. And for reasons that I'm not entirely sure of, they do not divide the degrees of freedom by 2. In any case, we'll just be able to apply this formula directly to get square root of 3 times 8.31 joules per mole Kelvin times the temperature of 500,000 Kelvin divided by the mass of hydrogen in atomic mass units is just 1. And from that calculation I get 3,530 meters per second. So I'm going to fill out this table a little bit more. The average speed to create the cloud, according to the Wikipedia article, is only 2,250 meters per second, while the average speed, according to the Pearson, was 150,000 meters per second. Meanwhile, the temperature of the bubble was given in Pearson to be 500,000 Kelvin, and the root mean squared speed of monatomic hydrogen in that case came out to be, here we have 3,530 meters per second. My feeling is that this 3,530 meters per second of root mean square speed is more consistent with this 2,250 meters per second than with this 150,000 meters per second. I think a blast of hot gas moving forward at 2,250 meters per second and having an ambient temperature that moves the gas at an average of 3,530 meters per second is not that this happens at the in the wave, but rather this is what is left behind after the wave passes by. So I think it's reasonable to expect that this 10 to 20 million year figure is probably more likely than this 300,000 year ago figure. Another reason to suspect that is that a blast that cleared out 99.5% of the material in space coming through just 300,000 years ago, there should be some kind of fossil record, I would think, of something like that. My first intuition says to go back and look at extinctions in history, but this seems to go from 50 to 100 without, or from 0 to 50 million years ago without any significant extinctions in that time frame from 10 to 20. So in either case, whether the thing happened 300,000 years ago or 20 million years ago, it doesn't seem to cause a huge extinction, and probably what I'm not taking into is that the sun produces its own bubble, like where the Oort cloud is, and if a supernova explosion happens far away, bringing a blast of material coming in at 2,250 meters per second, if these are just monatomic hydrogen, the sun is going to basically stop those before they get too close to the inner solar system. But could it stop a blast of molecular hydrogen coming at 150,000 meters per second? Would be necessary if the Pearson article is accurate. To answer that question, I'm going to look up the solar wind speed. And it says the solar wind speed streams off the sun in all directions at speeds of about 400 kilometers per second. 400 kilometers per second is 400,000 meters per second. So a 400,000 meter per second wind should stop a 150,000 meters per second wind with no particular issue. Besides being much faster than the wall that would be coming through, it's also probably quite a bit more dense at this position, because by the time it got to the sun from the center of this sphere, it's already gone about 10 light years. It's going to be a fairly dilute gas by that time. So I would say in this case, either one of the alternative hypotheses is a possibility. Did the gas come through 20 million years and cool very, very slowly? Or did it come through 300,000 years ago and cool very quickly? Well, in that great region of space, 300 light years across, where can the heat go? The only way the heat can be dissipated is by the fast-moving molecules to collide with something else that is moving, on average, slower than it. And the only way it can do that is really to collide with the particles around the stars themselves. So there may not be very much opportunity for gas in this region to collide with something and cool. But if there is one unanswered question, it is how do they estimate the temperature of 500,000 Kelvin? Is that 500,000 Kelvin there? Is that some kind of a calculated temperature, or is it something that they've actually observed through ultraviolet telescopes? Are they actually observing an ultraviolet glow coming from the ambient temperature of the gas, or are they estimating the root mean squared velocity of the gas and calculating the temperature from that? Because this textbook has a habit of giving temperatures. For instance, in the Earth's mesosphere, it tells us that the temperature of the Earth is around 200 Kelvin. The temperature of the atmosphere is around 200 Kelvin. Wikipedia discusses a higher level in the atmosphere called the thermosphere, where the highly diluted gas can reach 2,500 degrees Celsius, which would be close to 3,000 Kelvin, 2773 more precisely. Now, similar to the way the thermosphere is way, way hotter than the outer atmosphere, the corona of the sun reaches temperatures well over 1,000,000 degrees. On this chart, 100,000, 1 million, this is about 3 million degrees. Well, it says leveling off at around 3 million degrees Kelvin in the corona. By the way, it looks like that 3 million Kelvin would be associated with a root mean squared velocity of 8,648 per second, almost 9 kilometers. Now that's the ones that are embedded in the corona. These particles here that actually are part of the solar wind go 500 kilometers per second, which could be compared to the one I gave earlier, which was 400,000 meters per second, which is less than 500 kilometers per second, but still but in any case, this 3 million Kelvin region here doesn't give you anywhere near the kinetic energy that these solar wind has. Notice this chart tops out at 20,000 kilometers, while this description stops at 10 million kilometers. Wait, it's way, way, way higher. About 10 million kilometers above the photosphere, the coronal gas is hot enough to escape the sun's gravity, and it begins to flow outward into space. So that's a vast territory between 20,000 kilometers and 10 million kilometers. And by the way, the comet that came through the other day called Chaisson was well within this, only at 700,000 kilometers, which would be well above 20,000 kilometers, but well below the 10 million kilometers. So that comet got closer to the sun than the origin of the solar wind. In any case, the point I was making was we've got these 3 different examples of the thermosphere around the Earth at 2,500 degrees Celsius, the corona around the sun at 3 million Kelvin, the local bubble at 500,000 Kelvin, And in none of these cases do they describe how they measured this temperature or estimate. Now we have Wien's law, which tells us that the wavelength of a peak emission is proportional to 1 divided by the We've got the blackbody curve that shows us the intensity versus frequency relationship for an object that is emitting electromagnetic radiation as a function of its. We've got Stefan Boltzmann's law that tells us the power output of an object according to its temperature of a blackbody. We have Stefan Boltzmann's law that tells us the power output of a blackbody given its temperature. The trouble is, I don't think the thermosphere or the corona or the local bubble represent what we would call blackbody. My expectation is that a gas, a diffuse gas that really doesn't interact much with itself, would not produce a thermal spectrum at all. Only on rare occasions when the particles actually collide would there be any light. And there should not be a soft glow of a continuous thermal spectrum emanating throughout the. But these temperatures are estimated from some other means, based on something like thermodynamics, that the temperature is related to the velocity of. Unfortunately, I have not found any indication of how these temperatures are actually figured or observed or measured. So that remains a rather open question to me, a question that obviously does have an answer, but something that the authors of these, the people that have calculated these temperatures, have decided not to convey. Or if they have, I have not seen it. And it's probably not a secret, it's just something that they didn't think anybody would be interested in. And so it got left out of the text. Well, to wrap up, I guess what's fascinating to me here is how these minor differences between numbers could represent very different theories about the evolution of the universe. Two reasonably respectable sources with highly different numbers on a description of the same phenomena, with the only real agreements being how big the diameter of the thing is and what caused it, but having major disagreements about how much material was cleared out and how long ago the thing happened. Neither of the sources give you enough information to really determine why they think what they do. They just kind of state each of these figures as facts, and we're left to guess how they what they saw that made them think these things. Oh, I guess this is typical among most subjects. I've been spoiled by a background of mathematics and physics, and every detail being motivated by some kind of rational reason. A description of a calculation or measurement, etc. Well, that's all for now. Thank you for watching.